there are many topics that could be covered in a course in distributed algorithm. We here mention two important topics. We just said that a process may fail by just crashing and stopping execution. The algorithm presented in this course assume this mode of process failure. But there are other types of failure that we will discuss briefly in this unit. Byzantine process failure and corresponding algorithms, and self-stabilizing algorithms. So we have Byzantine process failure and self-stabilizing algorithms. So what is Byzantine process failure? Some processes might behave arbitrarily, sending wrong information or omitting messages. And there are algorithms that tolerate this kind of failure and still provide the service they want. In general, Byzantine algorithms that tolerate such failures only tolerate up to, but not including, 1/3 of Byzantine processes. This has to be contrasted to non-Byzantine algorithms, where they often can tolerate up to half of the processes or the nodes in the asynchronous model. So the other type of algorithms that we will not cover in the course are self-stabilizing algorithms. So what are self-stabilizing algorithms? They are robust algorithms that run forever, but the system might temporarily be incorrect and exhibit transient failure. These algorithms revert to correct behavior once the transient error disappears. That's to say, the system eventually becomes correct. So self-stabilizing algorithms have two properties. Okay? They have two properties, and these can be described as follows. The system as a whole can be either in a legitimate state or in illegitimate state. And a self-stabilizing algorithm has the following properties. Convergence, which says given any illegitimate state, the system eventually goes to a legitimate state. And the other property is normally called closure, which says if the system is in the legitimate state, so it will remain in the legitimate state. As we said, in self-stabilizing algorithm, the system can be either in a legitimate state or an illegitimate state. And if this describes the state of the whole system, so if this describes the state of the whole system, if we describe the legitimate state as the outer ring here, and the legitimate state as the inner ring, if we start from the illegitimate state, it will converge to the legitimate state and then stays in the legitimate state. What are the advantages of self-stabilizing algorithms? They are robust to transient failure. They don't need any initialization, in the sense that the algorithm can start at any state, maybe, and then it will converge. And self-stabilizing algorithm can be easily composed, which by this I mean a service composed of two self-stabilizing services is also a self-stabilizing service. Here is an example of a self-stabilizing algorithm called the token ring algorithm. So we wish to have one token at all times circulating among processes. That's what we want. But sometime, actually, there might 2 or more tokens might appear in the system. Okay, and this is because of errors. And the algorithm actually always eventually guarantees that there is 1 token in the system. So here you have 2 tokens, and then they will disappear, and eventually you'll have only 1 token in the system.